In this video, we're studying an object in uniform circular motion, and we're given a radius for that of 3 meters and a period for the rotation of 4 seconds. And as usual, we're going to assume that the object starts along the positive x-axis. And in the picture, again, I'll just give you a reminder of the radius. That was 3 meters. And then we're told that it takes 4 seconds to go around once. In part A, we're asked to get the centripetal acceleration of this thing, so the magnitude of that centripetal acceleration. And there are a few different ways you could go about answering the question, but what I remember most easily is the magnitude of centripetal acceleration is v squared over r, where v is the speed of the object and r is the radius of curvature. And then we can measure that speed by just saying, well, when the object goes all the way around the circle once, which is a distance of 2 pi r, it takes 1 period to get that done. And we square the numerator and we get 4 pi squared r squared over t squared. And the denominator has that little r in it. And we arrive at perhaps a familiar second formula for the centripetal acceleration. It's 4 pi squared r, canceling one factor of r, divided by t squared. And these are the things we were directly given in the problem. So I plug in 4 pi squared times 3 over 4 squared. And to 3 significant digits, I get a centripetal acceleration of 7.40 meters per second squared. In part B, we're asked to get the angular velocity. And so just a quick reminder, because we're going here in part C anyway, the formal position vector as a function of time for an object in uniform circular motion is given by an r cosine omega t I hat plus r sine omega t j hat. And this includes assuming that the initial position is on that plus x axis. The omega there stands for the angular velocity. And I know the period is going to be 2 pi divided by the coefficient of t in those trig functions. So this is how you relate the period and the angular velocity. And I find that omega is equal to 2 pi over t, but my period was 4. And that means omega simplifies to pi over 2, and the units on that are radians per second. Now this was sort of guessable just by knowing that the period was 4 seconds. If it takes 4 seconds to go all the way around, and I start at t equals 0, then t equals 1 would be right here at an angle of pi over 2. T equals 2 at an angle of pi. T equals 3 at an angle of 3 pi over 2. And then at t equals 4, we're back where we started. So just by looking at that picture, I can tell, yeah, this thing is moving at pi over 2 radians every time 1 second goes by. And I get the same answer either way. In part C, I'm told, again, assuming theta naught, the initial angle is equal to 0, which I've already done, compute and plot the position, velocity, and acceleration vectors at t equals 1 second. So my general position function is just given by plugging the numbers in to what I already wrote down in part B. The radius is 3. The angular velocity is pi over 2 radians per second. And I get a 3 cosine pi over 2 t I hat plus 3 sine pi over 2 t j hat. If I then evaluate this when t is equal to 1, that gives me 3 cosine pi over 2 I hat plus a 3 sine pi over 2 j hat. But the cosine of pi over 2 is 0, and the sine of pi over 2 is just 1. So I end up with a position vector of 3 j hat, which makes a heck of a lot of sense because the object is located at the top of the circle and the position vector points from the origin to the location of the object, so it has a length of 3 and points straight up. Next, I look at a general velocity vector for this object in uniform circular motion, and I have to take a time derivative here. So I get a negative from this cosine function, and the chain rule produces a factor of pi over 2. So I have a negative 3 pi over 2 sine pi over 2 t I hat. Then in my second term, that's a 3 pi over 2 cosine pi over 2 t j hat. Then when I imagine evaluating this at t equals 1, again, the cosine term is going to vanish and the sine term will be equal to 1. So I arrive at a velocity vector of negative 3 pi over 2 I hat. So this vector points exactly to the left, and this isn't surprising either. I know the velocity of this particle must be tangential to its trajectory, and I know which way it was moving, so it has to be directly to the left. Finally, we look at the acceleration as a function of time in general, and I take another derivative. The chain rule produces another factor of pi over 2. And I end up with a negative 3 pi squared over 4 cosine pi over 2t I hat minus, because I'm differentiating a cosine, so minus 3 pi squared over 4 sine pi over 2t j hat. And when I evaluate this at t equals 1 second, again, the cosine of pi over 2 vanishes. And in my j hat term, I get a 3 pi squared over 4 sine of pi over 2 j hat, but the sine of pi over 2 is 1. And so my acceleration vector comes out to just a negative number, negative 3 pi squared over 4 multiplying j hat. In other words, the acceleration at this moment in time points straight down. And this is what it means to have a centripetal acceleration. It's always pointing toward the center of curvature, provided this object moves at a constant speed and constant radius. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.